So we've got Albert Einstein saying that light is not just wave, but also a particle, which, by the way, is what actually won him a Nobel Prize, not relativity. We've got Niels Bohr over here saying that electrons are at discrete energy levels too. Enter Louis de Broglie, who says, what's really true? If waves can be particles, why can't other particles be waves too? He suggested that everything is a little of both, but they behave more like waves when they have less momentum. Electrons are pretty fast, but they're also really small. Maybe they can be waves too. De Broglie characterized a wavelength, lambda, that is a matter wavelength. The differences are subtle. Notice that this wavelength is related not to frequency, but momentum, indicated by p, which is a product of mass times velocity. De Broglie got a Nobel Prize for this work. George Paget Thomson, son of JJ, and independently studying the same thing, Clinton Joseph Davison, both got a Nobel Prize for proving it. All they really did was shoot electrons at slits and notice interference patterns as waves moved in and out of phase, showing that electrons had to have wave properties. You might be right in thinking that this is strange, because I've never noticed anything about me behaving like a wave. Turns out this is, again, only noticeable for particles that are very low in momentum. So if we do some math for some of the things we might think have observable wave properties, we find that momentum of many objects brings the de Broglie wavelength down to a point far below what we'd reasonably be able to observe. For reference, gamma rays are about 10 to the negative 12. So you can see that very large objects end up dropping down below the de Broglie wavelength, so that we'd only be able to observe a T-Rex embodied as mass. Similarly, Barry Allen, the Flash, is both too massive and too fast to have an observable de Broglie wavelength. He needs to be able to tap into the speed force for all of his relativistic tricks. Flying squirrels, not being particularly large or particularly fast, are a lot closer to relativistic effects, but are still about 20 orders of magnitude off from being observable in even the gamma range. An electron can vary in speed, of course, but taking the higher speed from our photoelectric experiment that we talked about last time, it has a wavelength of about a nanometer, observable as an X-ray. Slower electrons may actually be observable in the UV or the visible range. So if an electron can exhibit properties of a wave with a given wavelength, there should be places that they are in resonance, some distances that they can travel around an atom that will allow them to stay in phase. In 2 dimensions, this is a little bit easier to conceptualize. The circumference around the circle must be equal to some quantized multiple of a wavelength. So there are quantized values for wavelength that will actually work with a given n. The math that comes next is a little bit more strange to most of you because you haven't talked about angular momentum in physics. But if the de Broglie definition of wavelength is substituted in, the terms can be rearranged to show that mass times velocity times radius, mvr, the definition for angular momentum, which is often indicated as a capital L, is equal to some quantized energy n times Planck's constant over 2 pi. Since n is quantized, Planck's constant is constant, and 2 pi is also constant, angular momentum also needs to be quantized. So now we know from de Broglie's definition that not only could we have waves that exist at standing values of n, we also have angular momentums that exist at standing values. Recall that before we looked at 2-dimensional standing waves and saw that certain frequencies at discrete values could give us standing waves with nodes shown by the collection of sand. We also saw that there were some patterns that could be more complex at higher energy. We can think of this as somewhat analogous to how we see angular momentum coming into play in standing waves for electrons. We also pointed out earlier that just as we can have a variety of shapes in 2 dimensions for standing waves, we can have standing waves in 3 dimensions, and the math for them indicates a variety of shapes as possibilities as well. The model predicted by the de Broglie wavelengths applied to Bohr's model of an atom works perfectly, again, just for a hydrogen atom. But we aren't quite finished with our whirlwind tour of chemistry and physics. We'll take a pause here to talk about how we can actually measure frequencies of waves, because it places fundamental limits on what we can actually know about anything that behaves as a wave, particularly the ones with very small masses. And it also helps us to understand why it's so difficult to move from a model that works with hydrogen and 1 electron to a model that actually applies to the rest of the elements. Whenever we measure the frequency of a wave, we typically use a reference wave. particularly for very high frequencies. By combining these two waves, we create a pattern of moving between a maximum amount of constructive interference when they're in phase and a maximum amount of destructive interference when they're out of phase. This movement between in phase and out of phase effectively makes a new wave with a wavelength of 1 over the difference in frequency, which we call a beat. You can see that indicated in line C. Along comes Heisenberg, the one on the left side, not the one on the right, and says that this really matters if everything is behaving like waves. If we actually want to measure frequencies, the change in time, or the length of measurement, needs to be at least a beat. Otherwise, it won't be accurate. And a beat length, remember, is 1 over the difference in frequencies. But, since frequency is related to energy, this also implies that we're limited in how closely we can measure energy. If we multiply by Planck's constant to give us measured change in time times measured change in energy, we see that it's necessarily bigger than Planck's constant. This is also extended to wavelength and momentum by similar math. Another way of looking at it, by dividing both sides by time, is that unless you measure forever, the change in energy cannot be measured with infinite precision. Again, similar math gives limits to location and momentum measurements. So Heisenberg's uncertainty principle states that we will always have these types of measurements, energy, location, and momentum, limited by uncertainty. Remember, Planck's constant is really small, so this really only matters with very small particles, like electrons. So we can't really know the positions of electrons, and we have to deal with the probabilities of electron locations instead. The person that actually put together the Bohr model and de Broglie wavelengths was Erwin Schrödinger, of feline fame. Schrödinger said, let's treat these electrons as waves, and what's better, I can define their energy based on an equation for their wave, denoted as psi, the Greek letter that looks like a trident or pitchfork. People love to write out the equation as it is here and say that the h with the hat on it is the Hamiltonian operator, as if anyone ever thinks of anything besides Lin-Manuel Miranda when they say that. What it actually means is a summary of all the types of energy, both kinetic and potential, that are contained in a negatively charged particle in motion around a positively charged center. This is where Heisenberg is important. Many of those energies are dependent on position and momentum, which means that we can't know them exactly. This is also where the cat comes in. The cat is an illustration of quantum entanglement. In the famous thought experiment, Schrödinger has a cat in a box that may be alive or dead, but it is both until we observe it. In Schrödinger's equation, the energy, based on classical constructs like mass, momentum, and position, is related to the energy of a wave. The electron is both at the same time. Only when we observe it does it collapse into behaving like one or the other. Anyway, the wave function, psi, has specific solutions that explain the quantization that we see in hydrogen spectra. Cool. Schrödinger thought of these wave functions as literal waves, which is not how we think about these now anymore. There really wasn't a way to think about these based on physical interpretations of an electron. He got a Nobel Prize anyway. Max Born reinterpreted the waves as probability functions by squaring the wave functions, which gave real values from the complex, as in they include the square root of -1 complex, values of the wave function alone. The wave function equations that actually yield solutions have a number of values that can be changed and still give solutions. The principal quantum number n, which we saw even in our one-dimensional examples, the angular momentum L, which we saw emerge in our two-dimensional examples as also being quantized, as well as a magnetic quantum number m subscript L, or m sub L, and the spin quantum number m subscript S, or m sub S. Any solution of this equation will have some combination of these numbers at different values, such that each electron corresponds to exactly one set of values for n, L, m of L, and m sub S. And each of those same values correspond to exactly one electron. We'll talk about what each of these values means in terms of the periodic table in the next few minutes. The first of the quantum numbers is n, the principal quantum number. This is the quantum number that corresponds to n in both the Balmer and Rydberg equations that explain the hydrogen atomic lines, and corresponds to the n of the Bohr model as well. Just like in the Balmer, Rydberg, and Bohr instances, n can be any integer greater than 0. In chemistry, we can talk about this number many different ways. It's commonly used to refer to energy shells or electron shells, essentially the number of layers out from the center of the atom. That's a little misleading because the outer layers actually have a small probability of coming closer to the center with the node in between, overlapping with some of the inner shells. The diagrams at the bottom display the probability distribution at any distance. You can see that the nodes in n equals 2, the middle, and n equals 3, the right, match the number of nodes in the one-dimensional standing wave. You always have one fewer nodes than the n minus 1 equals number of nodes. The principal quantum number is also related to the period, or the row of the periodic table, although the middle of the table lags behind the tallest sections. The next quantum number, the angular momentum quantum number, has to do with the momentum in a circular system, like in a 2D or 3D application. We saw earlier that this value, given the letter L, is quantized just like n. In Schrödinger's equation, L can give us solutions only if it is a non-negative integer less than n. So if n equals 1, L can only be 0. This number corresponds to a specific subshell, which in turn are related to the shapes of electron probability densities that may be possible with a given shell defined by n. The shapes shown here are then the shapes to possible solutions to Schrödinger's equation. Many of the shapes are actually identical. The second row is all the same shape, barbells, all corresponding to the L value of 1. The third row all correspond to an L value of 2, and the last two rows are corresponding to an L value of 3. While the numbers are important to actually factor into Schrödinger's equation, most chemists are more familiar with the letters that correspond to the numbers. So for L equals 0, the shape is a sphere, and we talk about the subshell as an S subshell. For L equals 1, the shape is a dumbbell, and we talk about it as the P subshell. Most of the L equals 2 possible probability densities are shaped roughly like an X, and we call them the D subshell. And the L equals 3 F subshell has a wide variety of more complex shapes. Again, notice that since L has to be below n, the more complex shapes aren't possible until higher energies. The next quantum number that varies in solutions to Schrödinger's equation is the magnetic quantum number, m sub L. The magnetic quantum number is always an integer between negative L and L in the solutions, which means there are more possibilities as L gets higher, which of course is only possible when n also gets higher. Between n, L, and m sub L, we identify all the possible probability densities, with m sub L describing more or less specific orientations of those probability densities. Since these probability densities are distinct, and probability density is an awkward word, we refer to these specific probability densities as orbitals. Notice that when n equals 0, only L equals 0 or S is possible. Since S is L equals 0, the only m of L that is possible is also 0. That means there is only one s orbital that's possible, which we'll see when we relate to this periodic table. That's why the top row of the orbital shown is just one s orbital. When we have n equals 2, we can still have an L equals 0, an s orbital, but we can also have L equals 1 shown in the next row, p orbitals, with 3 specific orbitals corresponding to an m sub L of -1, 0, or 1. Whenever we have multiple values of m sub L, these values don't change the energy of the orbitals. So every p orbital has the same energy, every d orbital has the same energy, and every f orbital has the same energy. We call orbitals with the same energy degenerate, not because they're vile or reprehensible, but because in mathematical senses of the word degenerate, it's the opposite of generate. Instead of generating new energies, these all collapse into one energy, degenerate, degenerate. The final quantum number, m sub s, is the spin quantum number. There are only two possibilities, +1/2 or -1/2. Samuel Goudsmit and George Uhlenbeck proposed these two possible states based on very small differences in the energy of hydrogen atomic emission spectra at high resolution, called the fine structure. They envisioned these as arising from actual spinning of an electron, like the rotation of the Earth, which would induce a magnetic field and change energy, hence the name spin quantum number. Turns out this can't actually describe what's happening, but it's still the best analogy we have for something completely unique to the quantum realm. Technically, these quantum numbers exist independently of solutions to Schrödinger's equation. The first three variables give actual solutions yielding orbitals, and the spin quantum numbers refer to two possible states that an electron could exist in within each orbital. Gaudsmit and Uhlenbeck did not receive a Nobel Prize, but Wolfgang Pauli, who worked out the math and always envisioned this spin without classical analogy, lost the naming of the quantum number but did receive a Nobel Prize. By way of summary, we talked about four quantum numbers. N is the main or principal quantum number. It's generally related to the energy and sometimes called the shell. L is the angular momentum quantum number, and it corresponds to the subshell and the general shape of the orbital. M sub L is the magnetic quantum number and will refer to a specific orbital and a specific orientation. M sub S describes an abstract spin, which we think of as a direction of electron spin. It describes two possible states that can occupy an orbital. Together, these quantum numbers give solutions to Schrödinger's equation and a great description of what happens in hydrogen. In hydrogen, really only N changes the energy. L doesn't actually change energy at all in hydrogen, and M sub L doesn't change energy even in most of our simple atomic cases. And spin doesn't either. However, hydrogen only has one electron, and everything gets much more complicated when there are more electrons. So much so that Schrödinger equation only actually works for hydrogens, at least when Schrödinger first proposes it. When we get to real multi-electron systems, the position or possible positions of every electron influence every other electron. Since we can only know the probability of an electron in a location, not the exact location, the solutions to Schrödinger's equation for even helium are extraordinarily difficult. We also see that some of the energy levels change with the interference of other electrons. Notice that in this diagram, with energy shown vertically and individual orbitals displayed as lines, the angular momentum quantum number, L, actually has an influence on the energy. When n equals 2, which we can see as the number label below any set of lines, the L value, which is indicated by the letter that follows, results in a different energy. So P is higher than S in every one of these energy levels. You can see in the third row that D, corresponding to L equals 2, is higher than both the P and the S orbitals. So high, in fact, that they are higher in energy than even the 4s orbital with a higher principal quantum number. Electrons are like water, and they'll always fill the lowest places first. So if electrons are filling orbitals, they'll start with 1s, then 2s, then all the 2p orbitals, and so on. We can look at this diagram and see that. It's perhaps helpful to think of general rules for how things fill if we don't have this diagram. So we're always going to fill the s and p orbitals in a normal pattern. S first, because it corresponds to L equals 0, and then p, which corresponds to L equals 1. We'll follow the normal order of shells based on the principal quantum number. So fill the first shell first, and then the second shell. And since S corresponds to a lower angular momentum quantum number than P, we'll fill those before the p orbitals in a given shell. D orbitals have enough extra energy from the angular momentum that they will actually fill after the s orbitals of the next shell up. So within a period, you will have the d orbitals one quantum number behind. For example, the 4s orbitals will fill, and then the 3d, and then we'll go back to the 4p. The f orbitals have so much extra energy from the angular momentum that they don't fill until 2 orbitals behind. So it might look like 6s first, then we'd have 4f, then 5d, and then back to 6p. So in the 6th row, we'd go from a 6s, 4f, then 5d, and then back to 6p. You can see the relative orbital energy levels for all the orbitals that contain electrons in known unexcited atoms here. Notice our rule holds true. S and P always go in order, and then D comes after S, lagging 1 shell behind, while F comes between D and S, lagging 2 shells behind. So we've hedged around this for a while, but this all matters because it helps us to understand where electrons go in an atom, which in turn can help us to understand how they interact. Again, the electrons will always go into the lowest energy orbital first before anything else. This is called the Aufbau Principle, from the German word building up. This makes intuitive sense. Most things work this way. Water fills the bottom of a container first. A building's foundation must be built before the top. When we apply this, it means the lowest energy open spot available is where we put the next electron. Here it's a 1s orbital, and we've indicated by drawing an arrow pointing up. We know that each orbital can fit 2 electrons, as long as the electrons have different spins. We indicate that by drawing an arrow for the electron in the opposite direction. We can keep on going, adding new electrons into the 2s orbital, first with spin up, and whatever that means, and then with spin down. No alarms and no surprises yet. The next electron would go into one of the 2p orbitals, and it doesn't actually matter which, but most people put in the left one. The next electron goes into a different 2p orbital, rather than the same one. Remember that the p orbitals are all the same energy. They're all degenerate. But having spin opposing spin of opposite side in the same orbital gave slightly higher energy in hydrogen's fine structure, so having electrons fill up degenerate orbitals with all the same direction spin in different orbitals before we start doubling up actually results in slightly lower energy than filling up any individual orbital all the way before the others. This spreading of electrons across all degenerate orbitals is called Hund's rule. Similarly, the next electron goes into the vacant p orbital. Now that all the p orbitals have 1 electron, additional electrons fill up the p orbitals, one at a time. We see that when we fill the orbitals, we'll always have a unique address, n for the shell, l for the subshell, and m sub l to indicate which of the orbitals within the subshell, and m sub s to tell us what direction the spin is. The Pauli exclusion principle tells us exactly that every electron must have a unique set of quantum numbers. If we want to record the quantum numbers to indicate a specific electron, that's not a big deal. It's just 4 numbers. If we want to record a lot of electrons to talk about the electronic structure of an entire atom, we use a shorthand. Most of the time, we talk about every occupied orbital with just 3 characters. The principal quantum number of the subshell, indicated, the letter of the subshell indicated, for example, S, P, D, or F, and the number of electrons in the orbital or subshell as a superscript. So hydrogen's entire electronic structure is abbreviated 1s1. If we want to indicate a specific orbital rather than just a subscript, we can also use a subscript corresponding to that orbital. The subscripts that we use for p orbitals are x, y, and z. So we could have a px orbital, a py orbital, and a pz orbital. Well, we don't just do this for hydrogen. We can do this for any atom on the periodic table. Since the Aufbau principle states electrons will fill from the lowest energy first, we just start from the 1s orbital as 1s1 and add new electrons in order of increasing energy. So when we add another electron in helium, it's the other electron in the 1s orbital with the opposite sign. So now the configuration is 1s2. The next electron shows up in lithium, so it becomes 1s2, 2s1. Notice that the periodic table is arranged based on the orbitals that are being filled at any given time. The s orbitals are all represented by the leftmost 2 columns, with the exception of helium, and the p orbitals are all represented by the rightmost 6 columns. We talked about earlier how the d orbitals lag a period behind. You can see that they start with 3d orbitals in the 4th period, shown in yellow. Similarly, the f orbitals, shown in green at the bottom, are actually part of the main body of the periodic table. The first row, 4f, starts in the 6th period, just after the first d electron comes. I generally like to use the periodic table as a guide for which orbitals fill when, which requires remembering only that the d block starts with 3d and the f block starts with 4f. Others may find it convenient to draw a diagram like this. If all the subshells of the same principal quantum number, the one listed in front of the letter, are drawn in the same row, in the order of increasing angular momentum, that is S, then P, then D, as in this diagram. If you draw a series of diagonal lines from the top right to the bottom left, it will also show the order of filling. But notice this still requires you to know when the D and the F orbitals start, so it may not be that helpful. In addition to being able to write electron configurations, we can also use the periodic table to draw orbital diagrams. Hydrogen's electron configuration we've already talked about, but you can see an orbital diagram now right next to it. In an orbital diagram, a box representing an orbital is drawn with a label below it using the shell and subshell, here 1s, just like in the electron configuration. Each electron is indicated by an arrow, and each box, like the orbital it represents, can contain up to 2 arrows, up and down to indicate opposite spin. So hydrogen, having only one occupied orbital, would have its electron configuration written 1s1, and the orbital diagram would be a single box labeled 1s with an arrow. Convention is that the first arrow is pointed up, but that's actually completely arbitrary. So next, let's think about what helium's electron configuration and orbital diagram look like. Since helium is still technically in the 1s section of the periodic table, even though it's drawn to the right to represent a complete shell, we know that helium will be 1s, and since the second entry, it's the second entry of the 1s section, it is 1s2. Its orbital diagram is a single box labeled 1s with 2 arrows, one up and one down. Electron configurations are cumulative, so when we move into the 2s subshell with lithium, Li, we still have the 1s electrons that we had before. Now the orbital diagram has a second box labeled 2s with a single up electron. Try next to identify what the electron configuration and orbital diagram for beryllium Be looks like. Beryllium looks just like lithium, just with one more electron. Turns out this pattern continues. Each time you move up one atomic number, you add one proton and one electron. And so it'll have the same electron configuration as the element before, but with one additional electron. So boron's electron configuration looks the same as beryllium, except now it has a single 2p electron. Now that we have degenerate orbitals, we typically will draw all the boxes representing those orbitals in the subshell above a single letter for the subshell. Here, 3 boxes above the label 2p. Convention is that we occupy the orbital starting on the left, but again, that's completely arbitrary. With carbon, we just increase the superscript on 2p to 2 in the electron configuration. The orbital diagram represents the actual locations of electrons, so it's important that each box gets one electron, represented by an arrow, before any box gets a second electron according to Hund's rule. With this in mind, see if you can indicate the electron configuration and orbital diagram for nitrogen. You can probably see how onerous listing every single subshell gets as you move down the periodic table. Since most of the time only electrons of the outer shell are involved in bonding and reactions, we often will abbreviate all of our inner shells by listing the last noble gas, the elements of the far right of the periodic table, in square brackets, and then listing only the outermost shell after that, called valence electrons. So for sodium, Na, we don't list 1s2, 2s2, 2p6, and instead just put Ne for neon in brackets, followed by only 3s1. On this slide, I've included a bunch of practice problems and answers in Noble Gas Shorthand. Pause and try to give electron configurations and orbital diagrams for the listed atoms, and then continue to check your work. Feel free to use the diagram on the left for your convenience, but work toward being able to either recreate such a diagram or being able to use an unmarked periodic table for your guide. Electronic structure mirrors chemical reactivity. An electronic structure and chemical reactivity are both reflected in the groups of the periodic table. While there is some variation period to period, most of the groups, that is, the columns, within the period react very similarly to each other. For example, the first group, the one under hydrogen, each have one valence electron, a configuration so unstable that these elements cannot exist in their atomic state when exposed to air or water. Hydrogen forms covalent bonds with itself without being exposed to anything, and the remainder react violently with increased intensity as they move down the periodic table. Or, for a more widely familiar set of examples, the column on the right shows copper, silver, gold, and röntgenium, a group in the periodic table. They're curious metals, being relatively stable in elemental form due to their complete d subshell, but yet excellent conductors due to the single s electron. I pulled out 2 of the 32 columns of the periodic table, but the S, P, and D blocks are all strongly distinguished by groups. For this reason, we give names to many of the groups and sections of the periodic table. In most general terms, we separate the left side of the periodic table, except hydrogen, from the top right of the periodic table. The left side of the periodic table, all the way up to the gray, I think it's gray, section with Al for aluminum up top and Bi for bismuth on the bottom are all considered metals. Metals are characterized by being able to be formed easily. You can either pound or pull them into a shape, and they can conduct electricity relatively easily in elemental form. The top right of the periodic table, on the other hand, including the green, yellow, and teal sections, are all considered nonmetals. In between, you have the darker green elements, boron, silicon, germanium, arsenic, antimony, which is Sb, tellurium, and polonium, being intermediately defined as metalloids, being somewhat like metals and somewhat like nonmetals. Nonmetals generally form strong bonds with other nonmetals, and they give a wide range of properties and include many of the common elements in living organisms, like carbon, nitrogen, and oxygen. Within the larger classes of metals, nonmetals and metalloids, there are also several groups that have specific names. Starting on the left of the periodic table, we have the alkali metals. As we mentioned in the last slide, the alkali metals are extraordinarily reactive. This video on the left vivifies the veracity of this claim by showing the reaction of sodium and water to a tune that puts me in the mood for a little V for Vendetta. The lightest of these metals is well known in rechargeable batteries, and others are known in biological and diet applications, among many other applications. Totally worth the time. The next column over is the alkaline earth metals, which are in many ways similar to the alkali metals, but significantly less reactive. You can see in the left center that magnesium takes some time to react with even boiling water. The color here actually comes from a pH indicator called phenolphthalein, which turns pink when sufficiently basic, indicating the formation of magnesium hydroxide and hydrogen gas. These metals also play a wide range of common roles, including magnesium and calcium's biological importance. In the center are the transition elements, the kind of grayish ones. In broad strokes, they all have similar properties since the changes in electronic structure from one to the next are all in the d block, which is in the lower shell than everything else, and is generally less reactive than the s and p blocks. Even so, there are distinct group properties that are important to a wide range of inorganic, organometallic materials and catalysis chemistry. Many of them, and in particular chromium, form salt in a wide range of colors, which you can see in the bottom left.
I got all the blue ones.
This is the largest group of elements in the periodic table, now consisting of 40 elements, about 30 of which are stable. The nonmetals have distinct group names too, some well known, others less so. You are responsible for knowing the halogens, the penultimate, second to last group in the periodic table, with fluorine on the top, because of their high reactivity and importance in a wide range of chemistries. The halogens exist mostly as gases, but as you can see in the top right with the yellow chlorine as a gas, red bromine is a liquid at room temperature, but evaporates pretty easily, and purple iodine exists in equilibrium between solid and gas. It's sublime. The Noble Gas group is all the way on the right and consists of gases that generally avoid reacting. We use these a lot to talk about electron configurations. Knowing this group is mostly about building common vocabulary, although the unreactive nature leads to a number of important applications as well. The lanthanides, shown in light blue, and the actinides, shown in dark blue at the very bottom of the periodic table, are identified by rows rather than columns because they all correspond to the filling of f orbitals, which are sheltered so that they make very subtle changes to the elemental properties. For this reason, it is often difficult to separate one lanthanide from the next one and one actinide from the next. Incidentally, most of my longest held research interests lie with uranium and actinide and the lanthanides. This table gives a slightly cleaner display of group names. Notice that it also includes group 15, the pnictogens. The pnictogens are more familiarly and equally correctly known as the nitrogen group. You don't need to know that name though. It's seldomly used. Similarly, the chalcogens, group 16, are better known as the oxygen group, which is equally correct, and you also don't need to know chalcogens. We can draw electron configurations for ions in the same way that we drew them for atoms. For example, hydrogen starts with a 1s1 configuration, as shown. Metals and hydrogens tend to form cations, losing an electron to become as similar as possible to the last noble gas. So hydrogen here loses the 1s1 electron, now having no electrons at all, shown by the empty 1s box. Incidentally, H+ is something of a misnomer. H+ is usually attached loosely to something, even though it's convenient for us to think about it floating around on its own. Similarly, lithium, which normally is 1s2, 2s1, will lose an electron to become a lithium+. The electron configuration becomes 1s2, and the second shell becomes empty. Lithium+ now has the exact same electronic structure as helium, 1s2, and becomes similarly stable. We say that it's isoelectronic to helium. Try to identify what charge you would expect from beryllium, which begins with electronic structure as shown. Beryllium adopts a +2 charge, allowing it to become isoelectronic to helium and lithium+. When we have nonmetals, they tend to gain electrons to complete their shell rather than losing electrons. Look at the periodic table for chlorine and try to identify which element chloride, the name for chlorine -1, is isoelectronic with.